going to talk about two different things today. We are going to finish up Bitwise operations, and then we're going to do macros, which is a really important topic in computer science. So let's get cracking on that. So Bitwise allows you to manipulate individual bits inside of, let's say, an integer. Or since we've included cstdint, we could use a uint 32t, which is the same thing as an unsigned integer, but it'll never not be 32 bits. It'll always be 32 bits. If you say int in C++, there's no guarantee that the integer is going to be 32 bits under this standard. In practice, probably. In reality, that's preferable. So these two things are the same type, effectively. But if you move to a different platform, the top one here gives you a guarantee that it will always be 32 bits. And so this is preferable to this. Okay. So let's say that we've got, we want to, I don't know, pick up some items or stuff like that. Actually, let's start off by just reviewing Bitwise and, or, and not. So we will initialize this to 0. This is the same thing as saying x equals 0. You put the curly boys like that. So if we have, let's say x is equal to 4, and we've got y is equal to 2. I do try to mix up the syntax sometimes just to keep you guys on your toes. So what would it be if we counted x, and usually need the parentheses for this, by the way, because the double left arrow operator is a bitwise operator, so you run into order of operations problems if you don't have the parentheses. Like if you say, what is 4 left shifted twice? If you don't put parentheses around it, it's just going to print 42, right? And so if you want to actually print out 4 left shifted twice, it takes all the bits in 4 and moves them left twice. Good luck trying to do it without the parentheses. It's just going to print 42. Okay. So let's print out, anytime you print out anything and you're using bitwise operators, always use a parentheses. So let's say, what is x ANDed with y? Okay. So x in binary right now is 0, 1, 0, 0. Y is 0, 0, 1, 0. So if we go through and we bitwise and each of the numbers together, let's move it maybe down here like this. So x is equal to that, y is equal to that. What do we get if we bitwise and each one of the pairs of digits in these binary numbers here? What do we get? What do you guys think? We can do it like this also. 0b, 0, 1. This works as well. The 0b prefix means you're entering a binary number. Now I don't have to have the comments. And the people that said 0 are correct. Now what if we had this? So we've got 4 ANDed with 7. What is this going to print to the screen? Is it going to print 0, 1, 0, 0, or is it going to print 4? Right. The value is actually 4. What if we did an OR here? So let's say here x is 5, and that should be a y. Y is 7. What happens if you if you take x and OR it with, I don't want to say XOR, because that's a different operator, the XOR operator. But if you take x and you OR it with y, what do we get? When x is 5, y is 7, you take each one of the corresponding bit patterns and you OR each of them together, you are going to get 0, 1, 1, 1, right, which is just 7 again. Now if we did this, we would still get 7. So in this case, y is 3. This is the 1's digit. This is the 2's digit. So you go through each corresponding pair. 1 is true, 0 is false. You OR them all together. And we would still get 7 in this case. So JavaScript XOR and XOR equals true. Yeah. And so let's XOR them. Okay. So XOR means one or the other, or but not both, is true. So we're going to end up with 0. What is 0 XOR 0? So with XOR, it's true if one of them, exactly one of them is true, not both, and not neither. So what's the first digit here? 0 XOR to 0 is true or false? 1 or 0? 0 is correct. Good. And then we've got true XOR to 0. Is one or the other, but not both, true? Yep. Then the next one is also 1. Now for the last one, true XORed with true is false. Very good. Okay. And so this will output the 4's digits true, the 2's digits true, so this is going to output 6. And this is also why people get very, very confused if you ever type, what is 5 to the 3rd power? You know, people are like, okay, 5 to the 3rd power is 6. Wait. Right? Because people all think the XOR operator is exponentiation, and it's not. That is the XOR operator. It's a bitwise XOR operator. So students get very, very confused when they do that. In fact, that's why Easy Peasy will actually give you a warning, potential misuse of the caret operator. This is used for XOR bitwise operators, not exponents. If you meant to do exponents, use POW. Very common mistake in CSI 40. Okay, confusing the XOR operator and POW. All right, so let's talk about left shift. So if we take X and we left shift it 3 times, what do we get? Let's actually start off simple. If we take X, so if we have 101, and we move all the bits left 1, what do we get? By the way, there's programmer mode in Windows Calculator. So you can click on binary mode right here. You type 101, and then you just left shift it 1 time, and you get 1010. All the bits move 1 to the left. And so 1010 is 8 plus 2 is 10. So 5 times 2 is 10. So you can multiply by 2 by left shifting everybody once, because the 1's digit becomes the 2's digit, the 2's digit becomes the 4's digit. All the values inside of that binary number get doubled when you move them 1 to the left. Now what if you move them 2 to the left? What if we say take, let's update the value over here. No, not less than, double left arrow. Sorry, that was a mistake on my part. So if we take 5 and we left shift it twice, so we take 101, we move it left 1, it's 1010. We move it left again, what do we got? Got 101, and we move it left twice. 101, move it left twice. Not 10, it's the number 2. We're in binary mode. 101, left shifted twice is 101, 00, which in decimal is 20. So left shifting 5 twice, so 5 left shifted twice is equal to 20, because we essentially multiplied it by 4. Every time you shift it left 1 bit, it's a multiplication by 2. So if you shift it left 2 bits, you multiply it by 2 twice, 4. Anyone want to guess what 5 left shifted 3 times is in decimal? $40 is correct. I will also accept 0B 101 with 1, 2, 3 zeros after. Okay, same number. So, by the way, 42 is 101010. It's lol 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 in binary, which is the reason why 42 is the world's most perfect number. Okay, so X left shifted 3 times. Sorry, update it up here. X left shifted 3 times is 40. And again, don't forget the parentheses. If you forget the parentheses, this code will compile. And it will give you JavaScript level confusion. Instead of 40, you get 53. Because the order of operations, the cout with X happens first, which returns C out. Then it does a C out with Y, which returns C out, which then does a C out with end line. So it prints 5, then it prints 3, then it prints the new line character. So don't do that expecting to get 40. Anytime you work with bitwise operators in a C out statement, you need to put it parentheses around it because that double left arrow operator is left shift. Okay. Now what if we do right shift? If left shift if left shift, I just gave you the answer. If left shift is multiplication by 2, what is right shift? So 5 right shifted 1 time. Yep, it is division by 2. If you move the 2's digit to the 1's digit, you just divide it by 2. Now, what is 5 divided by 2? 5 right shifted once is 5 divided by 2. So what do you get? What's 5 divided by 2? Is it 2 or is it 2.5? Is it 2.5 men or is it 2 men? And part of a baby. So think about it. We've got 101 here. And we move everybody to the right. So what happens to the person on the far right? We got the 1's digit here. He's looking at the abyss. He's looking at the precipice. We push him off the edge. What happens to him? Falls off. Plays the Wilhelm scream. Ah! Right? So if we right shift this 1 time, then we just get 1-0. And that last one, ah! And in decimal, it's the number 2. So 5 divided by 2 is 2. All right, not 2.5. Very common mistake students make. They think the answer is 2.5. The answer is 2. Any bits that get shifted off the edge, they just fall off the edge of the world, like Dio. Okay, in Dio era Black Sabbath, right? Also, Heaven and Hell, the sort of Black Sabbath reunion with Dio and the Tiny Iommi and the other guys from Black Sabbath. Okay, so but what if we right shift it twice? What if we right shift 5 twice? So we had 101 before. We push everybody to the right, push everybody to the right. It is now 1. What if we right shift it 3 times? What do we have now? 5 right shifted 3 times. Zero is correct. We've thrown everybody off the cliff at this point. We got nobody left. Okay. So that is left shift and right shift or we haven't done not. Okay, so let's try this. So this guy is just going to be the number 1, and all I'm going to do is output the not of x. So all of the 1s become 0s, all the 0s become 1s. What number is 1 1 1 1 1 1 1 1 1 0? 31 1s and a 0. Anyone want to guess? Luke's the only person brave enough to guess the answer here. Pull up calculator. The answer is 0. 0. -2 is correct. Yeah, it's like, why do we get 0? It's bizarre. Yeah, the answer is -2. Right. So this is more of a CSI 45 topic, but So you know how you have like let's just say you're dealing with 4-digit numbers, right? And you have like 1010. This one here is the 8th digit. This one's the 2's digit. So that's 10. So how do you do negative numbers? Well, if you're doing negative numbers, the highest bit, instead of it being 8, it would represent -8. And so this number here, if we were doing signed 2's complement numbers, this number here would actually be -6. If this was a signed integer. That's why earlier I had an unsigned n, right? I had uint 32t because people will get baffled when you when you flip 1 and then suddenly get negative numbers, right? And so if you do this with an unsigned integer, then you're going to get something very close to max int, right? So 4.2 billion and change. Whereas when you have a signed integer, that top bit, if it's 1, instead of it meaning 2.1 billion and change, it means -2.1 billion and change. All the other bits have the same meaning. True story. You're going to study this more in CSI 45, but that's sort of the 30-second summary of how signed integers work. Whatever the highest bit is, instead of it meaning positive 2.1 billion in a 32-bit number, that's the highest bit, 2.1 billion and change. It represents -2.1 billion. All the other bits mean positive numbers. So when you bit flip everything, you end up with, yeah. So if you bit flip 0, anyone want to guess what you get if you bit flip 0? So you have all zeros, they turn into all ones. A lot. -1. Because think about it. Like, let's just take a 4-bit nibble again. So like, let's say you have 0000, and you flip this to 1111. The highest digit is the -8. So you have -8 plus 4 plus 2 plus 1. So that's -1. So the highest bit here is 8. That's 8. And then all this is 7. So -8 plus 7 is -1. Okay. The highest bit is the -8 bit. All the other bits are still positive. So -8 plus 4 plus 2 plus 1 is -1. So true story, whenever you have a signed integer, all ones, no matter if it's 4 bits, 16 bits, 32 bits, 64 bits, 128 bits, if you have a signed 2's complement number, which is what basically everybody uses, all ones means -1. And then that would be -2, because we're 1 below. You can kind of count backwards that way. All right, so that is that's Bitfields. That's kind of it. Let me go over like some handy things to memorize. If you're going to set a bit, if you're going to test a bit, if you are going to turn off a bit, there's some patterns you can learn, and you'll see these patterns all throughout what you might call lower level code. If you ever interface with the Linux kernel, for example, the Linux kernel takes, I know I showed you guys this last time, it takes this thing called flags, and each of the individual bits inside of the flags represents a different option, read mode, write mode, that kind of stuff. And so you have to be comfortable with bitwise ORing and ANDing and things like that in order to make these things go. Because instead of having 32 separate parameters, which you would have to look up all of them, like what does this mean? Should parameter 5 be true or false? Should parameter 6 be true or false? Instead of having to look up 32 different parameters, which would be ridiculous, you just pass in flags with like your 2 bits that you care about set. Let's leave everything else. So the pattern, to set a bit, looks like this. So acts. So when you set things up, you create everything in powers of 2. It's like in Quake, the weapons in Quake are stored in a single integer. And so axe is like 1, single barrel shotguns 2, double barrel shotguns 4. Everything's a power of 2. So each item is its own power of 2. So each item is its own bit in a binary number. So this is how you can set it. So you start off with weapon equal to 0. So it should be weapons. Yeah, weapons should probably be more correct. So you start off with no weapons. And then this line of code here says pick up the axe. In plain English, it would say pick up the axe. Hello, Ed. Hello, one.
Patty was asking if she could come over on Saturday.
We're going skiing on Saturday, girl.
You are?
Yeah, but Sunday's doable.
Shit, you can.
Okay. Well, I don't know. Sorry, girl.
I
So-
don't know that we're going skiing.
You're excited. I can see your excitement.
We also have Ellie's birthday party. We ain't gonna go.
Ellie's birthday party's Saturday?
No.
No.
Well, it's on Sunday.
Sunday.
Well,
Yeah.
her party is on Saturday, but on Sunday is.
Okay. All right. So, in plain English, this code here is pick up the axe, pick up the single-barrel shotgun, pick up the rocket launcher. Easy.
When are we gonna go skiing?
Tomorrow. We're going skiing tomorrow. It's the last day of the season.
When did we decide?
I don't know. I decided for us. Okay. So this is the pattern for how you set a bit on a bit field. So each one of these options here is a power of 2. So you just OR it, bitwise OR it, that turns it on. This pattern here is how you search. So if you say if weapon ANDed with weapon axe, then that is going to return true. If the bit corresponding to weapon axe is set, it'll be false if it's not set. So if you want to see if the axe bit is set, if the single barrel shotgun bit is set, etc., use the single ampersand pattern like that. And then to turn off a bit, use bitwise not with the ampersand. The reason why that works, like let's say the weapon axe is the number 1. So it's 0, 0, 1. So when you do the bitwise not on it, it turns into all 1s with a 0 at the end. 0 ANDed with anything is 0, so it turns it off. 1 ANDed with anything leaves it alone. So basically this line of code here is going to leave all the other bits alone, except for the bit corresponding to the axe, and it's going to turn that item bit off. So we have now dropped the axe. Okay. So if we currently have the single barrel shotgun, we spawn a backpack. So it's weapon single barrel shotgun. We delete the item off us, and so we can put an item down on the ground. And this is what code looks like when you have people working with bit fields. So it's just that those 3 code patterns you'll just see over and over again. Right, so like just looking through the man pages for open, you can see ANDed with a not. Like this is just how people code. Okay, you got to get used to it. And that is that's the end of Bitfields.